Hello, everybody. Welcome. Uh, this is Algorithms and AI, Artificial Intelligence, the Future of Communication. And I'm Dr. Jessica Eise, and this lecture is part of a short course that is an introduction to algorithms and artificial intelligence in communication. So the goals of this course are to help you develop the agility to work intelligently in digital environments and to stay on the vanguard of communication innovation. And also, I want you to be able to confidently approach digital topics with a base of knowledge and the ability to critically assess its impacts on communication. So this is the first of an 8-part lecture series. And today we're going to cover the topic of what is an algorithm. And my goal is to help you think critically. And to do that, I believe that we need to understand concepts, not just memorize them. So this course is not about learning how to program or learning how to write algorithms that control artificial intelligence. I definitely can't do that in 8 days. But it is just to teach you the foundational concepts of what these things mean so you can understand them and you can think critically about them. Because we won't all be programmers, but we need to understand these concepts so we can work with programmers and we can also understand how artificial intelligence and technology will influence the future of our fields. So to understand artificial intelligence, we need to understand algorithms. And to understand algorithms, we need to understand programming. And to understand programming, we need to understand some basics of a computer. So we're going to talk about the very basics of computers, programming, and algorithms today. And we'll start with a quote. People don't understand computers. Computers are magical boxes that do things. People believe what computers tell them. So perhaps these words might ring uncomfortably true. And I think we all agree that approaching programming and artificial intelligence while thinking of computers as a magical box that does things is maybe a little bit absurd, right? What are those things that it does exactly? And what is all that magic? And why do we believe what it tells us? So we're going to do a brief review of a computer. And we're going to talk about a personal computer or a PC, personal computer. And this is likely the type of computer that you're sitting at right now watching this video. So we're going to talk about what's inside your computer. So you have an air vent on the outside of your computer because what goes on inside your computer creates heat, okay, from your hardware. And most of that heat comes from a processor. So a processor is a piece of like mechanics inside your computer that's about 2 inches by 2 inches, made of ceramic, and there's a silicone chip in the processor about the size of a human thumbnail. And to explain these things, I'm going to use a lot of anthropomorphizing language. And anthropomorphizing means when you attribute a human characteristic or behavior to an object, right? I don't really love using anthropomorphizing language for a computer, which is why I don't also love the term artificial intelligence, but we'll talk more about that later. For now, though, I will use some of that language just to help us build some basic concepts. But keep in mind, a computer is not at all like a human being. In no way is a computer like a human being. So just always remember that. So some people call the processor the brain of the computer. It's the control center in a way, and it's where all commands are carried out. The processor is really important for programming. People also call the processor the central processing unit, or the CPU. All the commands that are issued to a computer through programming are compiled in the processor. So it's called the processor because it processes things. The CPU, or the processor, sits on the motherboard, or the main circuit board. So this is like a thin plate, which we might, if we're going with this human analogy, right, we could equate to a spine, right? And it links all the different components of a computer together. On top of this motherboard as well is the RAM. So RAM stands for Random Access Memory. And this is the place where a computer temporarily stores data, okay? It's like short-term memory. If you are working on a document, but you haven't saved it, it's stored here. If you have a bunch of different programs open and running, they're all here. You can imagine if you have a lot of stuff going on at once, the RAM can start to move a little slowly. That's why sometimes you might hear people talking about adding extra RAM to speed up their computers. So whenever your computer is turned off, all short-term memory disappears. So if you've been working on a document, but you never saved it, it will be gone. And I bet you've experienced that once or twice when your computer crashes and you didn't save something. Okay, so then you've lost it. So where does a file go then if you do save it? And it goes on the hard drive, okay? This is where software is installed, where documents and files are stored. The hard drive is long-term storage. So when you run a program or open a file, the hard drive sends some data over to the RAM. So the faster your hard drive, the faster the computer starts up and loads programs. A computer is separated into basically like two kind of terms or concepts, things that we usually talk about, which is hardware and software. So what I just talked about, the like bits and pieces of your computer that you like hold and touch, that's hardware. So they're the wares that are actually hard, right? The physical components of a computer. Software, on the other hand, cannot be held physically. There's nothing to touch, like, or feel or see. Software are programs and data that tell the computer what to do. I'm not super excited about the word software because it sort of implies that you can like touch it, that it's like squishy or something like physical you can pick up and look at. Maybe we might be better to call it controlware because it kind of controls what the computer does. But, you know, it is what it is. That's the term. So we have hardware, which is the physical pieces of the computer, and then software, which is what kind of controls what a computer does. So an operating system, let's talk about an operating system, is software. And an operating system, which in the words of one of my colleagues, is like a bridge between, and these are all imperfect analogies, but we'll do our best. So, operating system is like a bridge between the hardware and the user. So if you think of this like a car, the operating system is like the steering wheel and the brakes and the accelerator. So it allows you to like drive the machine, so to speak. That's what an operating system allows you to do. So often you may hear of an operating system called by its acronym, which is OS. So it's software and it lives in your hard drive, All major computer platforms require an operating system. And some of these most common operating systems, which you've probably heard of, are Linux, Windows, Mac OS. If you get it now, it's Mac operating system. The operating system for an iPhone is iOS, right? So iOS, I operating system. Starting to make sense, I'm sure. The operating system manages all the other software on the computer, which we might call applications, right? So it handles the input and output to and from the hardware. So my colleague described an operating system as a bridge. Think of the operating system as a bridge spanning a giant technological valley. You are on one side and the computer is on the other, and this operating system transports you back and forth across the valley so you can make sure the many tools and functions of the computer are working as you desire. So rough analogy, but just giving you the general idea. Some people, if they're very ambitious, which probably isn't anybody in this class, I don't think we have any advanced programmers in this class, but maybe you will be one day. If you're feeling very ambitious, you can create an operating system from scratch, which is made out of hundreds of thousands of lines of code. So you would want to learn naturally how to code before building your own operating system. And so this will take us now into programming. So we're going to start talking about programming. The history of programming, in a way, sort of starts with vanity, right? As so many of our inventions do. In the 19th century, the elite wanted beautiful textiles in elaborate designs. And Joseph Marie Jacquard, who was born into a French silk weaving family in 1752, met that demand in the form of a remarkable, programmable power loom, which you can see in the picture here. Weaving was once very tedious, and this loom really revolutionized that. And many wealthy aristocrats were delighted. So this machine became known as the Jacquard loom. And it was controlled by a set of cards that could produce patterns. Okay? And the series of punch cards, so the punch cards, controlled the threads. Each hole in the card corresponded to one row of thread in the design. So a simple design required maybe one card, but heavily brocaded materials required perhaps an entire deck of cards. So the Jacquard loom served as inspiration for Charles Babbage, who is best known for envisioning and creating designs for the analytical machine, or engine, excuse me, the analytical engine, right? And the analytical engine was a general purpose programming computing engine. And it has many of the essential features of today's modern computer. So programmable, a store where results could be held, memory, and a mill where processing was performed, so a central processor. Yet Babbage needed to figure out how he could get this great engine to do what it needed to do. So how could it serve humans? And this is where programming entered the scene, right? And he drew some inspiration from Jacquard's loom. Today we see computers performing all kinds of functions. We play games, edit photos, watch videos, write stories. But at the beginning, these computers were just envisioned, designed, and developed with the hopes of assisting in mathematics. So actually, you might not know this, but computers actually used to refer to people who were hired to do long, tedious mathematical sums. So a computer used to be an actual person who used to do tedious math, right? But now that's why a computer was like maybe a mechanized version of something that could do long, tedious math. Obviously, we've come quite a long way from that. So, however, but somebody had to envision that beyond that, and to do that was pretty radical and revolutionary. And one visionary was Ada Lovelace, who envisioned a computer that could do anything that could be noted logically. And this was back in the 1840s. So she understood and explained data and processing, and how you could take an instruction set and load it into a machine. So basically, conceptualizing the very essence of programming, which is taking a machine and giving it logical instructions so it can perform something that would meet a human need. And she envisioned even things such as playing music back in the 1840s. Quite impressive. So let's jump ahead from the days of Babbage, Lovelace, and Jacquard to World War II. And it was really during World War II when electronics advanced to the point where building computers became a possibility. This was a very exciting time for computing. I'm sure you've heard of Alan Turing, who created the Turing machine that became the foundation for theories about computing and computers. There's a very lively and curious and kind of tragically war-driven flood of ingenuity during that period. So in 1946, at the University of Pennsylvania, there is this machine, the Electronic Numerical Integrator and Computer. And the way they did programming back then was by plugging and unplugging a maze of wires so that it properly positioned row upon row of switches. And to do this, the government hired a handful of young women with math skills. And these early women programmers were known as computers. And they would painstakingly set up the machine by hand. So that was actually where coding started in the early days of computer development. You would plug in a wire, flip a switch. And while that's a simplified description, it was an extremely complex, tedious, and time-consuming job. After World War II, early stored program computers began to appear, which means that the handwork of setting switches and wires could be eliminated because programming instructions were placed onto punch cards or tapes and fed into the computer. So back to punch cards. So flipping switches and plugging in plugs is called like a low-level language. And it is commanding a computer in the most basic format. It's not hard to imagine how this must have become remarkably frustrating and limiting. This is in many ways because a human brain does not work in the same way as a computer. So it's not natural from the way that we're raised and the way our brains function to communicate or code in binary form. So let's talk a little bit about binary form. So you've probably heard of a 0 and a 1. Okay, a 0 and a 1 is basically the on or off. So it's the switch on or switch off. So switch is in 0 position or switch is in 1 position. Because the guts of our computers are made up of tiny switches, transistors, and other electronics. And these can either be in one of two states, on or off, or 0 or 1. And this is why we use zeros and ones, and this is why computers like speak in binary, because binary means 2, and there's the two states of 0 and 1. So I see streams of zeros and ones in so many graphics depicting computers. Today we have higher level languages that make coding easier, such as Python or Java. You may have heard of these. So the algorithm is the most fundamental concept in programming, and it is a very precise procedure to solve a problem. So it is a step-by-step guide with certain inputs to achieve a certain output, set of instructions to complete a certain task. Sometimes I say these things and I think they just don't mean anything, right, to people who aren't already familiar with algorithms and coding. So I'm going to give an example of an algorithm and how an algorithm does not or may not work in like human life, right? Because algorithms can be hard for humans to understand at first, because humans don't operate based exclusively on logic. And algorithms, everything about an algorithm is based on logic. In fact, as human beings, we can be fantastically illogical. We may try to apply logic to solve problems, but often, and sometimes we do, or our own particular brand of logic, right? So here's an example. Say that you have an algorithm for handling a friend who's upset, right? Let's say this imaginary friend named as Albert. So Albert is very upset. So you go into your head and you find your algorithm for handling a friend who's upset. And you follow your precise procedure to try and solve this problem. So the input is grumpy Albert, okay? And here is your recipe, your algorithm for trying to improve Albert's mood. Okay, so step 1, buy Albert a donut and a cup of coffee. Step 2, give Albert the donut and coffee and ask Albert what's wrong. Step 3, listen to Albert talk until he finishes talking. Step 4, smile, say, I hope you feel better, and leave. Okay, so your output, then you would think, would be Albert feeling better, right? But what happens? Albert does not feel better. Albert is furious. Why is Albert furious? Because Albert was upset because his girlfriend broke up with him yesterday at a coffee shop over donuts and coffee. And you just reminded him of that horrible experience. Okay. Albert's response is not like an output that we would have anticipated based on like the algorithm we had. This is because human scenarios and human interactions generally tend to be incredibly complex. This is why applying algorithms in human life isn't generally something that we do in the sense of like the way you would when you're programming or coding. So usually we're very responsive to like different outcomes, like reading facial expressions. Maybe everything we do is an algorithm, but it's just the most incredibly complex algorithm that imaginable, right? And so with another person, for instance, if you'd taken a different friend, let's say Amanda, and Amanda had been your input into this algorithm to make a grumpy friend feel better, maybe it would have worked, right? With this complexity of human beings. And this is why algorithms don't generally work on humans, because we are not logical and rational in the way a computer is, and we have feelings and context, and humans are not generally individually predictable, although it's much easier to predict a group. Like group behavior can be very difficult to predict individual behavior. Algorithms are the foundation of programming and mathematics and science, because everything in programming is logical. So a process or set of rules to be followed in a problem-solving operation is the essence of the field. Computers are machines, and machines are utterly rational. So let's talk about logic for a second here. Think of an algorithm as something like this. If A happens, then execute B. If C happens, then execute D. If D and E happen, then execute F. If F happens, then execute A. If A and B happen, do nothing. If B and C happen, execute D, E, F, G, H, I, J, K, L, M, N, O, P. Okay, this is an algorithm, and this is the logic that drives an algorithm. So if A and D happen, we don't have an execution function for that, right? So as the human being, we would need to program that into our algorithm. Okay, so this is kind of getting to the end. Algorithms can be extremely complex, right? And it's really amazing and wonderful how the brains of our sophisticated programmers operate in order to be able to translate our human desires into algorithmic functions. And these algorithms are implemented through lines of code. The code is compiled. The processor within the computer processes the code and acts upon it. And that's how we get our computer to do what we want it to do as humans. So this is the end for today. In the next lecture, we'll cover the basics of artificial intelligence.